So let's talk about a phase diagram of solids. We're going to talk about what's called the isomorphic binary phase diagram. So binary means two phases, or two constituents, I should say, not phases, but two constituents. And that basically means that we are going to have the ability now to talk about the fraction of something, right? So for example, I was talking about A and B atoms. A common example is, I think, nickel copper. So this is going to be the phase fraction, or it's not the phase fraction, the compositional fraction of nickel, either mole fraction. So anytime I write X sub N or X sub something, that is the mole fraction of that. Now, I drew a more complex phase diagram before, but the simplest possible binary phase diagram is called isomorphic. And isomorphic means one morphology or one structure. And that's because nickel, pure nickel, and pure copper are both FCC. And because they have the exact same crystal structure, and because they're relatively the same size and same electronic behavior, same valence electron behavior, we can have perfect solid solutions of copper and nickel at all compositions. So I can start out with 100% copper, start putting nickel into the copper lattice, and add more and more and more until we come over here and we have pure nickel. We start taking the copper out and we have a pure nickel. And this solid phase, which is 100% solid solution, we're going to call alpha phase. And we know also that if we go up to high temperatures, we can make a perfect liquid solution of copper and nickel as well. So we go up in temperature, and then between these, we have to have a two-phase region. So this is going to be liquid plus alpha. And this is the structure of an isomorphic binary phase diagram. And as I said before, these type of phase diagrams you can take and, at any point, for a given temperature, for a given composition, what is going to be present in equilibrium. And we can also take and we can now interpret this in terms of what's happening as the structure evolves. So let's say I take some copper and I know the moles of copper and the moles of nickel, I put them together and I heat them up and I melt them. Now I start cooling down. As I cool down, it stays as liquid. And at this point, I cross into the two-phase region of liquid plus alpha. Now, if you had pure nickel, I come down and I start out as liquid. I come to this point, it goes from liquid into solid, right? It goes from, pretty much I've gotten rid of this whole part of the phase diagram, and all I have is that single point. Liquid, solid, and that is the melting temperature of nickel. Over here, same thing. If I'm pure copper, I come down. At this point, it transforms into solid. Now it's solid. So that is the melting temperature of copper. But up here, I come down and I have liquid and I have solid, and it didn't exactly melt. It just started forming solid. And same thing, if we keep going down here, I touch that, and now I've transformed into alpha phase. So we call this line the line where our last solid disappears as we're increasing the temperature. We call this the liquidus. And the liquidus separates a two-phase region from liquid. And we call this line, which separates a two-phase region containing liquid and solid, the solidus. They're not really melting temperatures in the same way we think of here and here, but instead they're the point where we start to form solid and the point where liquid disappears. Okay, so we have this representation and we know what's happening here, but what's more is we can get a quantitative picture of what's happening as well. So for example, up here at high temperature, if someone were to say to you, what phases are present? We say it's all liquid, 100% liquid. What's the composition? Well, it's this composition, which I'm going to call this whatever X and I. It's just the particular composition that I'm at. Okay. If I go to cooler temperatures, I can also say what's present. So, well, it's all solid, 100% solid phase. And what's the composition? Again, it's pure Ni. Now, up here, though, if we say what phases are present, you say, well, it's liquid and alpha. Well, you can ask the question, how much liquid and how much alpha? That's called the phase fraction. And I'm going to represent that as an F alpha and an F subliquid. And the way that we determine that is we determine that using what's called the inverse lever rule. And let me show you how that works and explain to you why it works. So I'm going to draw this picture again. I try to make it a little bit bigger. So imagine this is going to be X and I. That's my particular X and I. Maybe I'll call it X and I star. And star means that it's the particular composition I'm looking at. Okay, now, first I'll just show you how to calculate it, and then I'll explain why. So let's say I come down to this point. That's some particular temperature. The way that I determine the phase fraction is I take the composition, I draw a lever through the composition that's parallel to the x-axis. I identify where the lever intersects the liquidus and solidus. And I want to call this X and I L for left. And I call this X and I R for right. And then what I do is I say liquid, the fraction of liquid is the distance of this lever. That's the lever that's away from the liquid. And that's why we call it the inverse lever rule. So it's that fraction, which is X and I R minus X and I star divided by the total lever length, which is X and I R minus X and I L. And the fraction of alpha, right there, again, I use the inverse. So I take the distance that's away from where it intersects. So I take that distance. So that's going to be X and I star minus X and I L divided by the total lever length, which is X and I R minus X and I L. And that's how you determine the phase fractions from the inverse lever rule. So let me explain to you why that works. Well, the reason it works is, if you want to think about it kind of from an intuitive perspective, liquid, alpha, alpha plus liquid. So at this point, I'm just above the liquidus is pure liquid. As I cool down, I'm now here. Now, if you want to ask yourself, well, is it going to be mostly liquid or mostly solid? Well, I'm still really close to that line. So I'm still going to be mostly liquid. And if I draw this lever, that is bigger than that, right? So that would be the inverse. And in fact, if I go, let's try to draw a little finer line. Let's say that I go up so that I'm at the point where I only have just like one little nucleus of liquid right here. At that point, I have almost, 0.000001% solid, and all the rest is liquid. And the same way, if I keep going down, and I come down, bump, 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 here, and I'm at the point right just barely above the solidus. Well, if I look at that, the closer I get to that, the less liquid there is, as long as I'm taking that little part divided by the total. So intuitively, you can think about this lever rule in terms of it showing the relative proportionality as we pass through the phase. So determining the phase fraction is the inverse lever rule. We can also ask ourselves, what is the composition of each phase? Right here. Well, the composition of each phase is determined by taking our lever, going over to the edge where it touches that phase, drawing the line down and reading it. So liquid has the composition where the liquid boundary touches the lever. So I want to say composition. That is going to be here, which is what we're calling X and I L. And the composition of the solid, that's where the alpha phase touches our phase boundary, which gives us X and I R. And we could ask ourselves, what's the total composition of our system? Well, the total composition is still X and I star. Right? We haven't taken anything in or out. All we've done is taken the atoms and separated them one to the other. But if we look at overall what's in our crucible or wherever we're melting this, it hasn't changed at all. And kind of a fun exercise is to prove to yourself that if you know this composition, and then you know the left and the right, you can get the phase fraction, and if you know the fraction of each, and you know the composition of each, you should get out the same total composition as you have just in the center.